Okay. Got it. Okay.
As per the statistical data, 48 had registered.
Okay.
And 20% of that means so we are approximately okay.
Oh, good.
Okay. Yeah.
I'm sure some people will join a little later.
So. Yeah, that's right.
Yeah.
Always. Okay. So maybe I can start and introduce you, and then probably you can.
Yeah.
Yeah. Because it's almost 5 o'clock. So let me welcome VG and Vinod Trivedi, who are and Damle for this session. For the time being, they are the persons from the participant side. Let me welcome Dr. Shantha Bhushan on Math Clinic platform. She is Associate Professor at Azim Premji University and holds a PhD degree from IIT Bombay. She has worked as a DST Fellow at IISER Pune and worked for an institute called Flame at Pune, and then for an NGO called Kalpavriksha. Okay. She is interested in math education at present, obviously. She is at Azim Premji University, so highly interested in math education. Her current project is to create resources for tensile and visual learners at the school and college level. She is going to talk about a very interesting topic, which we sort of see every day, an activity we do every day, maybe twice or thrice a day, and how that is related to mathematics. It's called knot theory. So her topic is explorations in knot theory, but for the middle school level. So that will be very interesting for us to listen. So Shantha, please.
Yeah. Thank you, Professor Rana and Math Clinic for giving me this opportunity. So I basically am thinking of this 1 hour of interaction that we have as a way for me to think more deeply about my work in knot theory and how it relates to what we do in school. So my topic is spatial thinking and knots in school. Okay. Yeah. Just a minute. I'm trying to go to the next slide. Yeah, okay. So when we think of knots, the things that come to our mind typically are things like shoelaces or phone cables or ropes that we use to hang clothes or sailor's knots, right? This is typically what comes to our mind. And the technical word for this that topologists use is open knot. So let us look at one more example. Yeah. So this is a example that I got from the Quanta magazine, which is capturing how a particular cable is, what are the forces acting on it as we tighten it. So these are two pictures that we have. And so you can see that the two ends of the knot are left open, right? So this is typically called an open knot. And from the physical point of view, these are very important. So whether it is a sailor's knot or whether you're, gift wrapping a book or anything else, and you want it to stay in place, we use a thread or a string and we fasten it. and the mechanical properties of the way the string goes over itself and holds it in place is of great importance. And sometimes it can be very cumbersome when we have phone cables, laptop cables, or intertwining with each other. But it is of tremendous importance to understand this from a very practical and physical point of view. Whether you take the umbilical cord or you take the optic fiber that goes from continent to another continent under the sea, these are all open knots. But this is not the study, or this is not the kind of knots that are studied in topology, right? It would be interesting to ask why. The reason is that for a topologist, what is important is what can be changed. And so if I take this knot which is there over here on the top, I can undo this very easily, right? So then it becomes just a straight piece of thread. So just for example, so I have this knot, I have this piece of thread. I just put it over and bring this. This is an open knot. I can easily undo it, okay? And then I get back the string. So essentially everything is a straight string, so it's not interesting for the topologist, right? So what do topologists study? Okay, so another example is of solar flares. There are many natural phenomena where we see knots coming up. So for a topologist, a knot is an embedding of a circle in R3. That is a fancy way of saying that we take a thread, we take a piece of real line, and then we just make sure that the ends meet and we get a what is called as a closed curve. Okay, this could also be a, okay, maybe yeah, this could also be a knot. This is also a knot, right? So anything that does not have self intersections and the starting point and the end point are same is called a knot. Here I've given a picture of a trefoil, and it is beautifully colored. So you can see that there are three parts of this closed curve. Closed curve basically means it starts and ends at the same point and it does not intersect. The way this picture is drawn, we can already imagine that the blue part of the trefoil curve is going over the green and red part, and then the red part is going over the blue and green part, and then there is a part, the red part of the trefoil knot goes under, right? So this is what we, from this picture, we are able to imagine this. So I will talk a little bit more about visual spatial visualization and spatial thinking a little later after introducing knot theory, right? So this is the knot theory studies what we call as simple closed curves in R3, right? So here are some beautiful pictures over here. So just let's take a minute or two to understand what is happening here. We see that there are knots, and there is some number that is given right below every knot. So for example, you look at the circle and there is 0, 1. You look at the next one, it says 3, 1. The next one says 4, 1. So any guesses on how the numbering goes? What would 3 or 4 be referring to?
Ma'am, does it refer to the number of curves?
Number of curves. This is one closed curve. We are talking,
so
there
the number of times we are twisting the rope to get the loops or something.
Can you define twist a little bit?
So when I have like when I have the rope in the first one, okay, which is a closed curve, and then I put one hand on one side, right? I put my fingers on one side and then I turn my other hand once, so that will be one curve. Then suppose I keep one hand steady and twist it again, that will be the second twist.
Okay.
So I am not sure whether I'm able to tell what I want to say.
Yeah.
But
So
I will say-
can we take that a little further? So can
Okay.
you just look at the thought you're thinking along the correct lines? If you look at the numbers given below in the table, there is 3, 1, 4, 1, 5, 1, 5, 2, 6, 1, 6, 2, 6, 3. So there is so there are, each label has two parts to it, right? So we see that the label with 3, there is only one. With 4 also there is only one. With 5, there is 5, 1, 5, 2. With 6, there is 6, 1, 6, 2, 6, 3. So can you take a guess as to what this 5, 6, 7 could be?
Could it be underpass and overpass?
Absolutely. Absolutely. So what is happening here is that in our mind's eye, so this picture is drawn in 2 dimensions, right? So just like if we take, if we take this curve here, this trefoil, you can see that the number of times the curve is going over another part of the curve, right? So you can see that we can describe this as overcrossing and undercrossing. So in our mind's eye, we are able to visualize the 3-dimensional picture, even though the image that we have is in 2 dimensions. Okay. So in this table here, what we are doing is the 3-1 says this is a knot with 3 crossings. Okay. The 4-1 says there are 4 crossings. 5-1 has 5 crossings. 5-2 also has 5 crossings, but there seems to be some difference between them. 6-1, 6-2, 6-3 all have 3 crossings. Okay. Then there are 7 with 7 crossings, 21 with 8 crossings. Okay. So a little bit about why would somebody want to do this? So let's look at a little bit of history of the origin of number theory. So the great mathematician Carl Friedrich Gauss, and he is my big hero. The origins of knot theory, I mean, of course, it goes all the way back to people representing knots in, through columns, rangolis, and many other things. But mathematically, if you see, Carl Friedrich Gauss, he has his notes with 13 sketches of knots. Then Listing started to think about knots and how to represent them. And then actually the big push for knot theory came when there was this theory that all matter could be described through something called ether. And Sir Thomson was thinking that all different kinds of materials. So sodium would have a different description in terms of vortices, and vortices are nothing but knots. And so there was a lot of excitement that you could think of like we have the periodic table with atomic number and atomic weight. So there was this very big enthusiasm trying to think of all matter described by vortices, but that was quickly dismissed by the famous Michelson-Morley experiment, and he dismissed the idea that there was something called ether. But the mathematical journey had begun, and people wanted to classify. So the table that we saw here is an attempt to put all possible knots. So in this list, we are saying that there is only one knot with 3 crossings. There's only one knot with 4 crossings. There are 2 knots with 5 crossings. So I'll get back a little later by what we mean by there's only one knot. Clearly in our mind, we can think of many ways of getting those 3 crossings, right? So when we represent, so we are representing a one-dimensional object, okay, which actually lives in R3. Now we are projecting it to a plane. And in this diagram, you can see that there are some breaks that are there, right? So is it clear what is happening? For example, when the strand goes over and the strand below goes under, there is a break. So you can make out, if you start at any point and you go over, you can see which is over, and then it comes under, then it goes over, and then it comes under, right? So this is called a knot diagram. So the way we get knot diagrams is we take the parametric representation of a knot in R3, we project it onto a plane. There are many planes we can project it to: XY plane, YZ plane, any plane. Some of the planes, the diagram may not look clear, but in most pictures, it will capture the crossing. One thing we notice here is that any point that there is crossing, there are exactly 2 strands that are crossing. We don't have 3 strands crossing or 4 strands crossing. If there is something like that, we move it a little so that at any point we just see this, only 2 strands crossing. So this is called a knot diagram. Okay, so here is an example of writing the same knot in different ways. So you can see that the trefoil knot, the picture that we took, if you take the point A and you can just throw it up, right, you get the second diagram. It is the same knot. We have not made any change in terms of cutting it or anything. It's the same knot. And here in the third picture, you can see that it looks like 2 twists and then the end points meet, right? So my point here is that the same knot, the pictures may differ, right? So for a given knot, we can have a large number of knot diagrams associated with it. So the question is, okay, so this is the earlier colored version that I showed. Here I'm showing the knot diagrams showing the overcrossing and the undercrossing for each of these knots. So you may ask, there'll be millions of questions in our head. So let's go one by one. Okay. So is there only one way of writing a knot with 3 crossings? That might be a question in your mind, right? And I showed the picture below. That is not the only way. So clearly, when I'm talking about diagrams, I'm somehow saying that something is equivalent, right? So what do I mean by that equivalent? So for example, these are 3 moves. So let's look at R1. So what happens is that there is a stringle strand that goes over itself, right? I can straighten it out. So if, for example, I have like this, okay, and then I can just straighten it out. So the knot is like this, and I just straighten it out. This is called Rydemaster Move 1, okay. On the other hand, suppose I have 2 strands going over each other. If you can see this, if you can see this. So now I have put, if it is like this, okay, both of them are undercrossings. I just pull it apart, it comes out, right, like this. So this is called Rydemaster Move 2, okay. And the third move, Rydemaster Move, is when you have a crossing, okay, you have a crossing like this, and then we have something that is, okay, just a minute, maybe I'll take this. Yeah. So if I have something like this, and then I have another part of the strand of the knot which is above, and then I just pull it and bring it below. So this is Rydemaster Move 3, okay. One might think that they are very natural because we are not doing anything to it. And this is a very deep theorem of Rydemaster, who said that this gives you, if I can use these 3 moves and go from one diagram to another, that basically tells me that the knot type has not changed. They are equivalent. So we have not formally mathematically said what is knot equivalence. 2 knots K1 and K2 are equivalent if I have a set of homeomorphisms that goes continuously taking one knot to other. So I don't want to introduce the word homeomorphism, but the theorem is that these 3 Rydemaster moves, if through these we can go from a knot K1 to K2, that is, then K1 and K2 are equivalent. Here is an example. Okay, so there are, let us look at the first picture. In the first row, we have, at the end, we have a trefoil knot. Okay. So through a set of Rydemaster moves, so in the first row, we are using Rydemaster move 3 from picture 1 to picture 2. Rydemaster move, just a minute. Sorry, Rydemaster move 2. And then we do 3 Rydemaster move of type 3, 2 of them. And then again, you do the poke and unpoke, you get back the trefoil. Okay. So then we say that the first picture is equivalent to the last picture. So in each of these rows, we have not done any cutting. Therefore, the knots that the diagrams represent knots that are equal. Any questions up to this point? Is it clear what I'm saying?
Just a small doubt. The images that are being seen just now. So, I mean, the string is knotted or it's open? I mean,
no, it is closed. It is a closed, simple curve.
Okay,
yeah.
Fine.
So let us think of knot as a simple closed curve. Okay.
Thank you, ma'am.
Here we have also introduced arrows to tell us in what direction we are moving, right? It helps us understand the picture better. So this is called an oriented knot diagram. So the point of what I'm saying is that, and this is a very deep result, is that to understand the equivalence of knots, it is enough to understand at the level of diagrams. And that's where the spatial thinking part becomes very important, is that we are starting with knots, we have some representation on the plane, okay, and we are able to manipulate those representations. So these diagrams help us think of what the actual curve would have been in 3 dimensions, right? So these are the Rydemaster moves. Okay, it's very easy to define that 2 knots are equivalent if we can find a sequence of Rydemaster moves that transforms a knot diagram K1 to K2. Yeah, okay. But the question is, how do we find if 2 knots are equivalent? Okay, so suppose we had not been able to do this job, right? We had pictures and maybe we were tired or whatever, we were not able to find the sequence of Rydemaster moves. Would that imply that the knots are not equivalent? No, that is not true. Okay, just because we have failed at something doesn't mean that. Okay, so the question is, how do we know, given 2 diagrams, how do we know that there is a sequence of Rydemaster moves or not? Does this question seem okay to everybody?
What what you are hinting at is probably what is a the word what is a intrinsic way of saying this is a knot, and what is an extrinsic way kind of thing.
Correct.
Extrinsic is where we can manipulate and physically do it. That may be called as extrinsic, because we are using our hands and such things, probably doing something. Possibly, I'm just trying to see as a layman what could be. And intrinsic could be, I just look at it and see some things and say that, okay, this is different from the other one.
Yeah, so I think that's right, sir. So when we take 2 knot diagrams, we if we are successful in finding a sequence of Rydemaster moves, then there is no problem. We say K1 is equivalent to K2. That means you can gradually take K1 and deform it nicely to K2 without any problem, right? Now the question is, suppose we are not able to do that, how do we find out? So this is at the heart of knot theory. This is a central question. How do we classify the knots? What are the tools that help us? Okay, so I am going to spend 5 minutes just talking about one way in which we can do this, which is very easy. Okay, so so there is now a definition that we make. We say that a knot is tricolorable if we can make it using 3 colors And at each crossing, either we use all 3 colors or 1 color. Okay. So for example, here we have beautifully colored it using red, blue, and green. Yeah, if you can just give me 1 minute, I will stop share here and I will need to use my yeah. So over here, I hope I can write. Oh, yeah.
Ma'am, can you keep it in landscape mode?
Landscape mode. How do I do that?
Is it an iPad? You can tilt it so that it will.
Okay. Sorry, this is not going well. I wanted to, okay, 1 minute. Let me just, yeah. Can you see this? Okay. Okay. So, 1 minute. Yeah. Sorry. Okay. Let me use the. So the tricolorability concept is the following. So we have a knot, we have an overcrossing, and we have an, sorry, we have an overcrossing and we have an undercrossing. Okay. What we will do is we will try to color it. So suppose I use red here. Okay. On the overcrossing, I use 1 color. Then for the undercrossing, either I can use the same color or I have to use the other 2 colors. So the requirement is that in the picture, okay, I have to use either, okay, so let me just write down. Use at least 2 colors. Okay, at least 2 colors. So suppose I have red, blue, and green. In the diagram, I must use at least red, blue, and green. And 1, 2 at each crossing. Okay. So if my color, suppose, is some color A, then I can do this. I can do B, C, or I can do the entire thing as A. Okay. So this is, if I'm able to do this, then my knot is tricolorable. This is the definition of tricolorability. Okay. And we can show that if K1 is and K2 are equivalent, then if K1 and K2 are equivalent, then either they are both tricolorable or they are both not tricolorable. Right? So we remember the definition of K1 being equivalent to K2 is that if I take the knot diagram, I take a diagram here, some diagram of K1, and I take some diagram of K2. We know that there are infinitely many diagrams. I can go from the diagram of K1 sequence of Rydemaster moves to diagram of K2. This is the definition. Okay, so I'll stop here and I will go back to stop share. Okay, sorry. Yeah. So this is the definition of tricolorability. Yeah. So what happens under Rydemaster moves is that tricolorability does not change. So for example, let us look at all the 3 ones. So when we untwist, if it is a single color, it remains a single color. Okay. When we have the second Rydemaster moves, it is called, some people call it poke. So then we had 2 separate strands of different colors. Then still the tricolorability remains. Similarly, in the slide move, we are very careful that all 3 colors are used or only 1 color is used. And by sliding, the tricolorability remains intact. Okay. So because of this, and the result that tricolorability does not change. If two knots are equivalent, they remain tricolorable or they're not tricolorable. Okay. So let us look at this. We have here two different knots. On the right hand side, however hard we try, we are not able to get tricolorability. It fails, right? Whereas in the first picture, we are using 3 colors to tricolor it. Okay, so we can safely say that these two knots are not equivalent. Does that make sense? Is everybody okay?
Yes,
Shantha, hi. Oh,
Yeah, hi.
yeah, I just wanted to ask that, like in the first diagram, what you're saying is that if there are parts to a certain loop, then those adjacent parts should not be of the same color. Am I right?
Yeah.
With regard to the concept of tricolorability?
Yeah. Yes, yes.
Okay.
So if you look at, let's look at the left side picture. You have the green arc on top. It's an overcrossing, right? So below that, we give different colors. And so the way to check tricolorability is we start somewhere, we start coloring, and we keep going to every crossing to get a consistent coloring. Okay. On the right side picture, however hard we try, there is a black thing. We don't know what to do with it, right? Whatever color we get, there seems to be a problem, right? If we put green, then it clashes with our rule. If we put blue, it clashes with our rule. If we put red, it clashes with our rule. So we say that the right-hand side knot is not tricolorable.
Right. Thank you.
Yeah. Okay. So this is a very deep concept. This idea is called invariance. What we mean by invariance is that if I have two knots, K1 and K2, okay, if they are equivalent, that means I have a sequence of Rydemaster moves taking K1 to K2, okay, in the projections, okay, then some properties remain unchanged. For example, if it was tricolorable, all the equivalent knots will be tricolorable, right? So we say that tricolorability is an invariant, okay? But we should not jump to conclusion saying that if two knots are tricolorable, then they are equivalent. The other way does not work. And that is the central job of knot theorists. Knot theorists are kept busy trying to find out how to distinguish. Okay, here the answer was the figure 8 knot is not tricolorable, so we got a quick answer. But suppose we had got both of them tricolorable, it still is not enough for us to conclude that these knots are equivalent. Does that make sense? Is that okay? Yeah. Okay. So we were talking about knots. These are simple closed curves. Okay. And why should we only talk of simple closed curves? We can take unions of two simple closed curves. For example, over here, these are two anklets. I'm able to undo them. So I started off like this. Now I'm able to put this. I have this. Okay. Such a thing is called a link. I have copies of circle. So there are two simple closed curves, and somehow the crossings have some relationship to each other. So we will call it a link. Now with these two circles, there are two possibilities. One is what I am doing. Okay. So it is like this. I'm not able to remove it, however hard I try. Okay. So this is one link. Another link could be that it's like this, right? This is also a link. The other one that I showed you just before this is also a link, but these are two different links. Okay, So we can ask the same questions that we are asking about knots. How do I know? I have two circles here. Okay, there are two crossings. How do I know whether the links are same or different? Okay, so there are invariants for this as well. Okay, if there is time, we will talk about this. But I want to spend a little bit of time talking about how we should think about this in our school curriculum. Okay, so I will come to this thing. Okay, before that, I just wanted to show you one thing. This is a picture. This is a gray surface with a yellow boundary. Is this clear to everybody? So you can clearly see that there is a crossing on top. There is a crossing here. And at the back, there is one more crossing. Okay. The boundary of this surface is our trefoil knot. If we were to hold our hand, a finger, and trace the boundary of this surface, we would get a trefoil knot. So another way of thinking about surfaces is as the boundaries of some surfaces, right? So these are two different ways of looking at knots. Okay, so I want to talk a little bit about our school curriculum and yeah. So there are a lot of math educators who are currently thinking a lot about visual reasoning, visual thinking, spatial reasoning. This is a quote from Bowler's Seeing as Understanding. So in that it says, geometry occupies a special position in the mathematics curriculum. It is a presentation of abstraction from visual and spatial experiences. For example, fields, patterns, measurements, and mapping. Geometry learning is very closely related to students' spatial intelligence. Okay. So this is as teachers of maths at the undergraduate and school level, all of us understand that there are different kinds of learners. There are some learners who are good with when things are given visually. Some people are good spatial thinkers, right? And I feel that when I especially look at undergraduate students and ask them about the toughest part of their curriculum, the answer that we get both in the interviews and informal chat with our students is that geometry, especially coordinate geometry, is the hardest. And I feel one reason why this happens is that we don't have enough experiences that are curated for students at the school level, especially middle school onwards. It's a lot of abstraction, a lot of representation in 2 dimensions, without enough experiences for the student to understand the relationship. So, so spatial thinking is something that we need to worry about on what are the experiences that can enable this, right? So, for example, in school curriculum, we think of polygons as broken straight lines that is closed. So, a square is a polygon with 4 sides. It's a broken straight line, and it joins the starting point and the ending point are same. And slowly we teach our students to even think of the enclosed area. We also study 2-dimensional objects in 3 space, such as cube. And first we look at the surface of the cube, and then we also think of the volume that is enclosed. So both these concepts are taught in school curriculum. However, I think one of the difficulties people like Janaki who have experience will be able to add about the representation of 3-dimensional objects in 2 dimensions seems to be a big place where students struggle. So we don't have enough experiences for that. And therefore, the spatial visualization, that is using our imagination. Some people use the word mind's eye to think of objects, to keep them in our brain, to see the relationship between various parts and what is happening. and to use a two-dimensional representation to visualize the 3D. For example, whether we use nets or whether we use origami, these are all spatial visualizations, and we need to pay more attention to spatial visualization. Okay, so I'm now going to give 2-3 examples. So this is actually the main focus of my talk, is to give some examples of how we can get more experiences for our students. So there's something called the cat's cradle. Here is a picture of this. I think many of us have done this at in school. Yeah, 1 minute. Yeah, so we can take a piece of thread and then just cut it and join it. So this is an open knot. Now I'm making a proper knot, by proper meaning the way the topologists use, by joining the two ends. Okay. So this is called an unknot. So various things are done using various games are played. So you can see this. So for example, you can, I'm not doing any cutting. I have the same closed curve. I am bringing it to this form. Okay. And then if I put my fingers and bring out one of the loops, no, sorry. There's a way of making this into a teacup. Yeah. So I didn't do any cutting, right? I did a smooth, nice deformation of the closed curve, and I have got this. So in this process, what is happening is we are using our tactile way of thinking to represent an object and to understand it and to help visualize it. So there are many games that can be played. This is a teacup that can be made by one person, right? So in the picture where I have shown on the PowerPoint, there is a crisscross that has been made. So there are 4 crossings that you can see, and they are held at 4 points. So what happens over here is that through a sequence of moves, and now the sequence of moves we were doing is exactly what Rydemaster has done, right? So we were transferring one part. So when I take a finger and I take the strand over to the other part, or I do this, all we are doing is these Rydemaster moves, right? So this is one way of trying to incorporate spatial thinking using games. So this is one example that I had. There is another game which Japanese mathematicians Kawauchi, Hayaka, and one more person. So I'll just send the link. Maybe if you can all go to your phone. Okay, the link is here. Let me just, yeah. I'll just send this link on the chat. Copy. Okay, we can just take 2 minutes to, sorry. Okay, it stopped share. 1 minute. Can everybody go and look at this? And did everybody get the link?
Yes.
Yeah.
Yeah. Can you just go to the link and you go to the website and you will see some games. Can you just click on any one thing? So the rules of the game are the following. So there is a knot. There is a knot diagram. Okay. and the crossings are all colored. Our job is to press on the regions between, and when you press on the region, you will notice that the crossings change. Okay, so the motto of the goal is to try to get all the colors to be the same. Are you able to access it? Is Janaki, are you able to see this?
Yeah, we can see.
Yeah. So anybody, any luck with? Can we just all of us try to? Can you see the screen that I'm sharing?
Yes, ma'am.
Yeah.
Yeah. Okay. So over here, this has already back to okay. So if you can see here, there are three purple dots. All the crossings are colored. Okay. So if I go to the outside region and press, what's happening? Can you see the color change when I pressed in the region in between? I pressed here, the color changed. If I press on the outside, oh, it doesn't allow. So the object of this game is to have all anybody successful? Okay. So here we got all the three crossings with the same color.
Ma'am, can you repeat again what exactly we're doing in this game?
Yeah, so the rules are the following, okay? We see that this is a diagram, okay? There are crossings. So in this case, all the three crossings are purple in color, okay? Or whatever, pink in color. If I go to some other diagram, okay, let us take this diagram. Okay, you can see that there are 8 crossings. There are 2 colors, either white or pink. So the game allows us to take our cursor and click on a region. When you click, all the crossings in that region, so I clicked at the bottom most, there were 2 pink and 1 white. When I pressed it, it changed color. It became, what was white became pink, what was pink became white.
Okay. And then our aim is to make all of them in the same color?
Yes, yes.
I see.
So if you go here, so now I have 4 pink and 4 white vertices. Okay. If you click on the outside in this particular thing, okay, all the vertices that, so the 4 corner vertices are touching the outside, the unbounded region, right? So they change color. Right? Then if I go to the top, did everybody
so
get the rules of the game?
Yeah. So what should be the algorithm? Like, how are we using some crossing number technique?
Okay. So first, the rules of the game are clear. We want all crossings to be of the same color. We start with a picture that has some coloring. Okay. Now, the knot theory part of it is that the pink may be over crossing and the white may be an under crossing. Okay. We just use colors to represent it. Okay. The game is, so in this game, Okay, so let me think of it. Suppose we gave this to a child in, I don't know, 4th or 5th or 6th standard. Okay, we said these are the rules of the game. Okay, what do we expect the student to do? We expect the student to first they will try at random. Okay, then they may, for example, you can press the region outside. So when I press the outside region, all the 4 vertices at the corners change, right? You can see that 3 pink, 1. So I'm changing, right? So this is the first thing they will figure out, that there is something called an unbounded region. So we take any knot diagram. For example, over here, we have regions that are inside, and then there is one unbounded region. Is that okay?
Yes.
Yeah. So now the reason why this game is so exciting is that there are many questions that we can ask. Okay, at this point, we can ask how many regions. So I got this closed curve. Okay, we don't have to tell the students anything about closed curves. We have a picture, we have certain crossings. So they notice that there are some regions. So we can ask to count the number of regions, to describe the number of regions. Are they bounded regions? Are there unbounded regions? How many unbounded regions are there? Here we have only one unbounded regions. Everything else, so 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 bounded regions, and the outside of this diagram is an unbounded region, right? So that is
Shantha, I just want to ask, I think it will be also some smart kids may also ask, like that problem of squares inside squares, no? So whether you want disjoint regions or non-disjoint kind of thing. No?
Yes, absolutely.
That will be very interesting.
Yes, absolutely. So yes, thank you, sir. So the kind of questions that will come from this would be a rich source of explanation. So Rana sir already said about, how do we count the regions? Are we, what if one region is contained as in part of another region? Okay, so we can ask here. I have 8 crossings, right? And I have, say, 10 regions. If I took another diagram with same number of crossings, would I get same number of regions? What then I can ask, suppose I know that it is 8 crossings. What is the minimum number of regions? What is the maximum number of regions? Then we could ask a whole lot of questions about understanding the plane itself. So my point is that we should think of games that encourage this kind of thinking of visualizing and understanding the space itself. We don't need to talk about a knot or its knot diagram, nothing. We just start with this game and we can do this. So this is one game that which I thought could be included in middle school. There is another game which is slightly okay. So 1 minute, I will go back to now. Sorry. Yeah. Okay. This is another game that has been tried out. In fact, at our Pi Day, we tried this. So the game is very simple. There are 4 students. There are 2 strings. Okay. In this picture, you can see a yellow and a blue string. Okay. Now, what can happen is that people can exchange with the partner who is standing next to them. So, and then if they do that, there is a twist that happens in the between the yellow thread and the blue thread. Okay. This is one thing that is allowed. The other one is that all the 4 people can rotate, say, by 90 degrees at the same time. So these are 2 things that are allowed. And the game basically says that you do these 2 things and you will come up with a final, the 2 threads will cross each other many times. Okay. Then we ask, so we can ask a couple of questions. Once this tangle has been made, we can ask another 4 students to take over and ask them to bring it back to the original configuration, right? And one might think that this, is a fun game, because basically you have to undo everything that the previous team did, okay? And you have to carefully analyze what are the crossings, what happens when we do a right turn, what happens when people on the same side exchange with each other. So you have to undo this. This is another wonderful game, and it takes a lot of time to actually unentangle. Now, one might think this is a very, it's a good game for spatial thinking, but what does it have to do with knot theory? The thing with knot theory is that DNA also can be thought of as a rational tangle. So over here, you can see the green and red strands, okay? This is exactly like the game that was played over there. Such a thing is called a rational tangle. Tangle because things are tangling. The rational word comes from a very deep concept that is linked to this, which is that we can describe any of these tangles by a rational number. So how to do that can be the topic of another talk, but the way to represent a DNA tangle, okay, and then to understand the mechanism. So there is some enzyme called typoisomerase which cuts things. So there are knot theorists who have studied the unknotting mechanism of DNA by representing it as a rational tangle. So my point is that we can make games out of things that serious research mathematicians work about, and these games can be incorporated into whatever they are doing, and can be the source of exploration. We don't have to give away all the answers. So this is the second example. The third example I was not able to write here is there is a game in which you write a diagram and one person tries to keep it knotted and another person tries to keep it unknotted. And there it becomes a very game theoretic situation where we can ask, whether there is a winning strategy and things like that. But those are for the slightly advanced, maybe 11th or 12th standard. It doesn't form in middle school. So I didn't write it over here. So that's what I wanted to communicate about the possibilities of using knots and strings to explore spatial thinking. So yeah, that's what I wanted to say, and I will stop here if there are any questions.
Thank you, Shantha.
Thank you.
Yeah, I think let us open the floor to the participants. You can unmute and show your video if you like, ask a question, discuss, make comments, anything you would like to, about the topic, of course. I think Shantha has touched many aspects of knot theory on one side and its relations with developing various understandings for students. So I'm waiting for others to.
May I?
Think. Yeah, please say your name and ask.
Yeah, my name is Brunda Ghorpade and I am a middle school teacher. So I'm a math science teacher and I teach standard 5 to 7. So basically, in a class, there are always about 80% of students who hate maths and about 20 who like maths. But then I think if we teach in this way, maybe they will get interested, because like for those who don't like maths, it's always about solving some sums and getting it wrong, and then the difficult concepts are taught and then they haven't understood the basic concepts and they go on getting confused. So I feel this is a great way to start with. I mean, even if we start with lower standards like second and third, with simpler knots, and then go on increasing the complexity, this could really help the students. And thank you so much, ma'am.
Yeah, thank you. Thank you. Yeah,
on my side, I just feel that the real challenge is taking this kind of activity for a class of 50 or so. So again, I mean, we can work out on that. We have to be a bit creative and resourceful. Otherwise, it was a wonderful session. Thank you so much.
Thank you. So actually, answering that question, Vinda, we tried the second activity of rational tangles for our UG students, and it took about 45 minutes or so. That activity really worked. The other one, the game called Region Select that I showed you, the website that I gave the link to, that also kind of is a fun way. And this is, the people don't even realize that it is maths, right? We can ask all these questions and it can be more like a conversation. And these can be taken outside in, say, you have a free period, or you have a math club or something like that. These are fun discussion sessions. I totally understand your point about time constraints. I understand that. But yeah, I think we should do our bit to, try this visual thinking and spatial thinking. Yeah.
Anybody else has a suggestion?
Janaki, hi.
Yeah, hi.
Janaki.
Hi, hello, sir.
Hi.
Yeah.
Welcome.
Thank you. I'm not switching on my video. I'm not really very well. So,
Okay.
but I attended this. I really liked it very much, Shantha. And I think there's a lot of potential in integrating this. One may have to think, one may take out certain time. Teachers should take out certain time of their, teaching time to do these kind of activities, even if they don't directly link with a particular topic of the curriculum. That is what I feel, my first observation.
Yeah.
And secondly, these kind of explorations have multiple parts of inquiry. So they should, they fit in very well in terms of exploration. So I think definitely we should try these out in the classroom. And also now, there's this whole talk about, linking mathematical and computational thinking. And these string activities which you nicely demonstrated, they can be unplugged, the so-called the unplugged activities which lead to computational thinking. Because those require tasks which don't require memory or formulae or specific procedures, and more exploratory, hands-on and things like that. So I think that also works very well.
Yeah,
and thanks a lot.
Yeah. Thanks, Janaki, for raising that point. I think there is this bit of algorithmic thinking also. So if we took complicated diagrams, first is to figure out whether there is a solution. How do you know there is a solution? If you figure that out, then how would you systematically go about changing all the colors? This really builds in algorithmic thinking and strategic thinking. So yeah.
Also in that region selecting is very interesting. Now, what could be the minimum number of clicks required to make all the crossings? That also could be an exploration.
Yes, absolutely. Yeah. So I'm saying that for conversations with the student, these are great starting points. So
Math talk can easily be started with this kind of activities.
Yes.
Thank you, Janaki. Anybody else has a good question, suggestion? If not, let me be the last one. I just want to give you an input, which will be very useful for the classroom as well as from the point of view of the topic. So let me share my screen and then show you something.
Yeah.
So here is something called GeoGebra, which almost all of us know. And there are beautiful activities developed for knot theory. So here is one I have just picked up. Okay. For example, it shows all the knots. Okay. The knot 01. For example, if I click it, it shows the knot 01, right? Which can be sort of rotated around. So you see, when students do these kind of things, their 3D thinking, spatial thinking sort of automatically comes in, kind of thing.
Yeah.
A triform. Now you can rotate it any way you like it, right? You can try to, there is another one like where you can extend this thread on any side, kind of a thing. Stays triform, right? So these kind of things, I think are, so integrating GeoGebra into, this is the 4-1 knot.
Yeah.
So You see, nowadays kids love something with technology.
Yes, absolutely.
If you you can take up this book and go to the GeoGebra classroom. Vrinda asked, how can we sort of do it with 50 students? You can have a GeoGebra classroom on knot theory. Okay. So take up some knots and try to see whether one can deform to one to the other or kind of thing, or give some, even if I can give some dots, okay, and say that now you could try to construct a knot, which is a trifle knot or some such thing. So many things are possible with GeoGebra. I have not explored everything on GeoGebra on this, but I think for knot theory and enticing students to do something will be very interesting with it.
Yes.
So one can build actually a session on GeoGebra and knot theory. So let me just stop sharing. Where is gone? Yeah, I think so. So that others can.
Sure.
You are sharing. Stop. Okay. I was just looking where is my. Yeah. So anybody else still has a question to ask? So the GeoGebra thing, you can just always search GeoGebra and knot theory. You will get n number of n bigger than or equal to 5 at least of applets will be available. Modify suitably so that you use it effectively in teaching and learning.
Yes.
That's my suggestion to you.
Yeah. Thank you, sir. Thank you. That was really
welcome.
Yeah.
Anybody has a still something? If not, let me thank Shantha for turning my thinking cap on and doing something, because nowadays I wait for such kind of activities. And thank you, Vrinda and Janaki, for joining.
Thank you, sir. Thank you, ma'am.
Thank you.
Thank you so much. Thanks a lot.
And,
Bye.
And take care.
Thank you.
And, we'll have some more sessions by Shantha later on. Okay.
Yes.
Thank you, sir. Thank you. Bye.